Okay, so here's another one. We have a reaction where we are given the equilibrium constant. So Kc is equal to 2.4 times 10 to the third. And we have a 1 liter flask that's filled with 0.6 moles of nitrogen monoxide, and we want to know what the equilibrium concentrations of all of these species are. Okay. Would you all like to try this one out? So feel free to work on that for a few minutes, talk to your neighbors, and then we'll regroup and work together. All right, how's this one going? Okay, so again, we want to make sure we're using concentrations in our ice table. And we're given an initial concentration of 0.6 moles of NO in 1 liter, so 0.6 moles per liter. Okay. And that's, other than Kc, that's all we're given in the problem. All right. So there's no initial concentration of N2 and O2. All right. For our change, we're going to have minus 2x for nitrogen monoxide, again, dropping down that stoichiometry. Okay, so we have 2 NO decomposing to form N2 and O2. We're going to have plus x for N2 and plus x for O2. So at equilibrium, we're going to have 0.6 minus 2x for the concentration of nitrogen monoxide, x for N2, and x for O2. So we can then solve for x by plugging these values into K. All right. Did everyone get to this point? You feel comfortable getting there? Hopefully. Questions on getting to there? Yes? The denominator is squared because of the stoichiometry in our equilibrium. Yes. So, yeah, that brings me to easy mistakes to make. One is forgetting to use the stoichiometry in the change line. Another is forgetting stoichiometry in K, so we're using that as the power. And the third one is typically not using concentration in the ice table itself. Okay, so watch those three things. All right. How do y'all feel about that equation? So we can solve that equation. Okay, that's a quadratic. So we could use the quadratic formula to solve that. Feel free to moan. It's awful. We all have graphing calculators now, right? So, well, many of you do. If you don't, that's totally okay. This is actually a really nice equation because it is a perfect square. And if you have a perfect square, that means you can take the square root of both sides of the equation. So if we do square root of 2.4 times 10 to the third, and the square root of x squared over 0.6 minus 2x squared. And by the way, this numerator is x squared because we have x times x. I hope I didn't just rush through that for you. This means we have 49 equals x over 0.6 minus 2x. And now we can much more easily solve for x. Okay, so I took the square root of both sides. Okay, so now if I multiply the denominator by 49 to get that on the left side of that equation, didn't mess it up that time, we'll have 29.4 minus 98x equals x. So we're going to add 98x to both sides. 29.4 equals 99x. Divide both sides by 99 to solve for x. And we'll get x equals 0.297 moles per liter. We're not quite done yet. But are there questions on that algebra? Which I don't know. Did anyone solve it with the quadratic formula? Did you get the same answer? You get two answers, right? Is one positive and one negative? You got 0.3 and then 0.296. Okay. So if you do the quadratic formula and you get two answers, sometimes one's positive and one's negative. You use, most likely use the one that is positive, right? But you said your answers were 0.297 and 0.3? Yeah. Okay. So let's take a look at both of these options, because you may get to a point where you want to use the quadratic. All right. Recall what our next step is going to be. We're going to figure out equilibrium concentrations. So let's look at the concentration of NO at equilibrium. It's 0.6 minus 2x. Okay. Usually it's not 3.301 or something like that? That's better, thank you. 0.303. It's important. Yeah. So what's going to happen then is that we're going to get 0.6 minus 2 times 0.303, which would give us negative 0.006. And you can't have a negative concentration, right? So that makes the 0.303 solution to the quadratic not possible. So it would have to be the other one. Okay, so I believe on the exam you will be given the quadratic formula. So that is a method for solving these types of problems. For this, like if you can recognize the perfect square, I mean, personally, I would rather solve it without using the quadratic formula, but again, that might be because I'm old and I don't use a graphing calculator, okay? But this is the way to do that, okay? Questions? Okay, so we figured out that x is 0.297. So we'll look back at our equilibrium line, and we'll find that the concentration of N2 is x at equilibrium. So that means it is 0.297 molar, as is the concentration of O2. And then the concentration of NO, using the correct solution to the quadratic, is 0.6 minus 2x, which is 0.6 minus 2 times 0.297, and we'll get 0.006 moles per liter. One of the really nice things about equilibrium problems, despite the fact that they have a ton of algebra, is that often you can check your guesses. So we wanted to make sure that we calculated these equilibrium concentrations correctly. We can plug them back into the equilibrium constant expression and then see if we get the correct value back out. So we